And I'm also very excited about the program. You're going to be exposed to the frontiers of particle physics. So if you'll be very lucky to attend these lectures. This amazing lineup of lecturers, and I hope you will get everything that you can from this opportunity. So I want to also just say that during this school, we're going to have 2 colloquia on Wednesdays at 2 p.m. So one by John Turney on magnetic monopoles, and the other by Christophe Gourgian on physics beyond the standard model. And those colloquia are part of the school, but are also for the whole institute. So it's going to be an interesting experience. And other announcements is that you'll find in your folder some information about places to eat around here. It's not difficult to find places to eat around here. We have many places where they have this per kilo system. Maybe some of you know, some of you don't know. And in addition, if you need lockers to leave your stuff, you can actually there's some lockers on the first floor, and you can get a key from the secretary, Umberto, and you have to pay a deposit, but just make sure you return the keys. We are also planning a social activity, which is going to take place this Wednesday, so the day after tomorrow. It's going to be a dinner together, everybody together at a restaurant. You'll give you more information, but it's going to be Wednesday at 7 p.m. I also have to apologize myself. I have to travel today, but I'll be back next Saturday, okay? So I'll be here for the second week of the school. So I think with that, I will pass the microphone to Professor Matthias Neubert, who is going to say a few words and is going to chair this session, this morning session.
Yeah, thank you, Rogerio. On behalf of the MITP, it's a great pleasure to welcome you here for this first joint school. Rogerio was already mentioning it. The MITP was founded in 2013, almost 10 years ago. We celebrate next year our 10-year anniversary, also with a special symposium in May. It is an institute like the institute here, basically, where people from the community can propose activities, workshops, conferences, also summer schools, and then we rank them and fund the ones that are the most compelling. And in particular, this year, 2022, we run in total 36 weeks of scientific activity. So it's a very lively institute, pretty much like the ICTP-SAIFR here. In fact, ICTP-SAIFR was our first international partner. We have collaboration agreements with this institute soon after we founded the institute, and then also with IPMU in Tokyo, Japan, the Tata Institute in Mumbai, and Fermilab. So the idea of these agreements is to do frequent exchanges, but also jointly organize activities, and this is the first joint activity that we're organizing. There's a sad history to this, because actually we started discussions with Eduardo Ponton, who was a very famous physicist and faculty member here, I think back in 2018. Then Eduardo got very sick and passed away at a very, very young age. And then we had in mind, of course, to run this school nevertheless in 2020, and then you know what happened, okay? So we had to postpone several times, but I'm very, very happy that it finally takes place. The idea of the school is really to bring together the European and South American particle physics communities as far as the next generation is concerned. So really to connect you, as you sit here, with each other. And it's jointly organized, as you see from the team of organizers. It's also jointly funded. The ICTP, of course, is giving all the local infrastructure and takes care of your accommodation, and MITP is supporting the travel of the students from Europe and also of all the lecturers from Europe. And I think this is a great model, actually, and many thanks to Gustavo and Rogerio for helping on the organization side from your institute, but also to the administrators, Shandira, who I think won't be here these 2 weeks, but helped a lot in preparing the school, and Umberto, who is doing the local administrative support. On the MITP side, there's going to be Felix Yu here, who's a faculty member in our institute. He will arrive Wednesday morning. and there is Oli C, who is in charge of the administrative support. So as you can imagine, organizing a school is always a big deal. You start basically at least a year in advance, and lots of work for many people. So the purpose of a physics school, I don't want to call it summer school, it's more a spring school, as we learned last night. So jackets are still useful, even though I think tomorrow we get a summerly day. But the purpose of these physics schools is really threefold. First of all, it's part of your graduate education, and it's a very special part because you're going to get lectures here from people who are world-class scientists, really leaders, each one of them leaders in their fields. And that's, of course, a fantastic opportunity. But then equally important is that you can meet these outstanding scientists who are just nice, ordinary people, like most of us, right? We're nice people. Even being an outstanding scientist, one can still be a nice person. And you can meet these people informally, socially, during the dinner that we have on Wednesday, during the coffee breaks, during the lunch breaks, right? And make use of that opportunity. Just ask them, talk to them, ask them about their careers, you know, what they lived through to become successful physicists. And thirdly, and probably most importantly, you will connect, and that's the whole idea of the school, you will connect amongst yourselves. And I think all of us, older people here, know how important physics schools is because you meet people who you know for life, at least, you know, life as far as your academic life is concerned. And so, for instance, I met Gustavo in Tassi many years ago. I will not mention the year, but you know, we have been good colleagues since then, and the same is true for many other people in the community. The reason is, of course, that also you are selected very carefully and you belong to the best students. So many of you will go on to make successful academic careers, at least that's what we hope. And so you will meet each other again. And in fact, you know, some of my own students from Mainz. We have 3 people here, not my own students, one of them, of course. And I know that already there are other people here and you know each other from previous other schools. So this is the way it works, and I think this is, in the end, the most lasting impact that these schools can have. Okay, so with this said, I guess all of us from the organization, we really hope that you have a fantastic time here, both scientifically but also personally. That you really enjoy these 2 weeks. If there's anything that you don't like, let us know, right? I mean, many things we can help, so just talk to us if there's anything that bothers you. And other than that, really enjoy the next 2 weeks. Wish you a fantastic time. And I guess with that, we will officially start the school by calling the first lecturer. The first lecturer is one of my former colleagues. I spent 7 years on the faculty at Cornell and was actually engaged in hiring Csaba. Csaba Csaki is a full professor at Cornell University and is really a leading expert in physics beyond the standard model, has contributed an enormous number of ideas in the field, really also often moving in new directions when old ideas didn't work, trying to find new clever ways. And his lecture course here will be on naturalness-motivated physics beyond the standard model. The name suggests that there will be, it's not unnaturalness-motivated, but there will be Gilad Perez in the second week talking on other ideas on physics beyond the standard model. But Csaba really will kick it off today with the first lecture in this course, and I wish you that you really enjoy and learn a lot from this course. I think I will. Csaba, please, the floor is yours.
Can you hear me?
Yes.
Okay. What is this?
For the camera.
Oh, for the camera. Oh, it's following me. Great. All right, very good. So welcome, everybody. Thank you so much for coming to these lectures. So as Matthias said, I'm going to be giving this series of lectures on sort of the naturalness-motivated theories beyond the standard model. So the plan is to first try to understand, what the hierarchy problem is, what naturalness actually means, why we care about that. So that will be the first topic, so the hierarchy problem. Can you see? It's big enough? Okay, and by the way, feel free to ask any questions anytime. The whole point is to, have people actually, understand things. So that's why I lecture on the board also and not from slides. So hopefully it will be slow enough for everybody to be able to follow, but fast enough to get a lot of things done. And after that, so that's maybe will be half an hour today. After that, I will start focusing on the two big sort of traditional directions for solving the hierarchy problem, which is supersymmetry. So that will be one of the big topics that we will try to discuss in great detail. And I will try to give you, sort of, a complete introduction to, what it means to have supersymmetry, and then how do we build the supersymmetric extension of the standard model, what the problems with those models are, where the state of those theories is. And then, so this will take probably more than 2 lectures. Okay. And then I will talk about composite Higgs and extra dimensions. So that's probably mostly Thursday and Friday. Okay, so that's essentially the plan for these 5 lectures that are coming up. And then, of course, we are going to have Rafael. So these are sort of, I would say, these are the traditional approaches to the hierarchy problem. And then you will hear some non-traditional approaches, more modern ideas, related to sort of cosmic scanning of parameters, relaxion, etc. So that's going to be covered in the lectures of Raffaele Dagnolo next week. All right, very good. And I should also add that I won't be giving handouts, but I do have lecture notes on these topics online. I think, I gave it to the secretary, so she may have posted it. But again, I have, I would say for this one, I had the TASI. There's some sort of a resonance here. TASI 2016 lecture notes. Those are online, and so you should be able to find them on the archive. And on this one, so this is with Ofri Telem and Sal Lombardo and myself, if you need to search for it. And then this one is from a CERN school with Flip Tanedo and myself. There's some sort of interference. I can also speak without the microphone. I usually speak loud enough, but it's better if it's fixed, I guess. It's also for some people are looking at it on Zoom, or? It's recorded. Okay. Very good. So let's get started. So the first topic of discussion is the hierarchy problem. And so I would like to understand, what the hierarchy problem is, why we worry about it, and then again, just give you the broad classes of type of solutions that we are thinking about before, starting to discuss, some of these specific ideas. Okay, so the hierarchy problem. So we are talking about, of course, the standard model, and we know now, of course, we didn't know beforehand when these ideas were first coming up, that there's an elementary scalar in the standard model, the Higgs boson. Higgs in the standard model. And so it's an elementary scalar, and it has some potential, and we usually parameterize it in the simplest possible way that we can. So we write some sort of a potential. We write a mass term and the quartic self-interaction. Yes, so this H is supposed to be a complex two-component doublet under SU2. Yes, so it has 4 components, as usual. And the important point about the hierarchy problem is that you can go ahead and start calculating the quantum corrections to the Higgs potential. Okay, so you can start calculating the corrections. So you write down some 3-level term. Okay, fine, but you know that the Higgs has to have all kinds of interactions because it plays many roles in the standard model. It gives mass to the gauge bosons, it gives mass to the fermions, so that implies all kinds of couplings, and also should have a self-interaction. Yes, without the self-interaction, this potential is not going to give the right vacuum expectation value for the Higgs scalar. Yes, so it has to have all kinds of interactions, and those will give corrections to the Higgs potential. Okay, so in particular, so you can start calculating the correction to the 2-point function of the Higgs. Yes, so I just write this dotted line as the Higgs. So in particular, at one loop, there will be a correction from the interaction with the fermions. Okay, so here, there will be Yukawa couplings that are showing up, yes, because the Higgs is the one that is responsible for the fermion masses in the standard model, so it has to have Yukawa couplings. So this diagram has to be there. There's no way around that. It has interactions with the gauge bosons, and so you can close up those loops. It will have self-interactions, so you can close up those loops as well. Yeah, so this is proportional to Yukawa couplings, and because the top quark is the heaviest one, so that's the one that has the largest interaction with the Higgs. Yes, this will be the largest contribution from the fermion sector. Yes, because the heavier a particle is, the bigger the coupling to the Higgs boson is. So this is usually the dominant one, since the top is so much heavier than the bottom. Yes, the next one is already like a factor of 50 down. Okay, so this will be proportional to the gauge coupling squared, the standard model gauge coupling squared. Here you can have W's and Z's running in the loop. And then this will be proportional to this quartic self-interaction of the Higgs. Okay, so you start calculating these loops, in usual quantum field theory, in perturbation theory. And how do the leading terms look like? Yes, well, you see that there are 2 fermionic propagators here, or 1 bosonic propagator over here. This is an integral, a loop integral, so you have a d4k over 2 pi to the 4. Yes, and then what you're going to have is essentially just 1 propagator, 1 over k squared minus m squared. I'm just writing it very schematically. What exactly is this angle? Here it's probably the top quark mass. Here is some gauge boson masses, but that's not the important point for now. Yes, what is important is that, as you can see, this, so the leading contribution to this 2-point function is going to be quadratically divergent. Okay, so this is going to be quadratically divergent, so it's going to be proportional to some mass parameter that for now I'm just going to call the cutoff of the theory. Yes, so this integral is divergent, so I'm just going to cut it off at some scale. So this is the cutoff scale of the theory. And the contribution to the Higgs potential, specifically, so this is quadratically divergent, so there will be a term that is of the form lambda squared times H absolute value squared times the mass term. So in the potential, there will be a term like this. Of course, there will be some coefficients here, and in particular, I wrote down the exact expression, what you will get for the shift in the Higgs boson mass. Yeah, so you can think of it as the shift of this parameter. Maybe I should call it delta mu squared. Okay, and that is equal to lambda squared over 32 pi squared. So that's the loop factor. And then there will be contributions from the Yukawa couplings, the gauge couplings, and maybe, are we supposed to give homework or? What's the, because I saw there is some homework session at some point. Okay, so maybe, you know, just getting this formula exactly is probably a good homework problem, g prime squared plus 6 lambda. Okay, so that's the leading term. Of course, there are other contributions, yes. There are finite contributions, there are corrections to wave function renormalization, etc. But this is the most important one because this is the largest one. Yes. So again, so this is the biggest contribution, and it contributes to the Higgs mass parameter of the theory. Yes. So now the question is, what should we make of this? Yes. So lambda, again, is the cutoff of the theory. Now, if you think that this cutoff is really big, and that's something that we should be discussing, what we think, how large it is, if the cutoff is much bigger than, you know, whatever the relevant mass scales in this system are. Yes, what are the relevant mass scales? Well, there is the physical mass of the Higgs boson, the mass of the W, the mass of the top quark. All of these are of the order of 100 GeV. Yes. So if this cutoff is much bigger than, you know, whatever the weak scale is, let's say 100 GeV or a TeV, let me call it a TeV, yes? And I call it a TeV because, you know, there's a loop factor here, so if lambda is a TeV, then the correction itself would be of the order of 100 GeV, yes, because you get here naturally a suppression by a factor of order, you know, let's say, you know, 10 squared, which is 100, so you get a little bit of a reduction because of this loop, but not much. So if lambda is much bigger than a TeV, then these loop corrections, these quantum corrections to the mass of the Higgs are much, much bigger than the observed physical mass of the Higgs. Okay, so then delta MH is much, much bigger than MH. Okay? And, you know, this is something that we know what it is. We know now by experiment that the mass of the Higgs is 125 GeV. Yes. So what the hierarchy problem is essentially telling you is that, what the hierarchy problem is that if you just take the standard model as is, then the corrections to the mass of the Higgs boson want to be much, much larger, many orders of magnitude larger than the Higgs boson mass itself. Okay, so quantum corrections want to pull up the Higgs mass to whatever the highest scale is that you can imagine in the theory. And that sounds a little bit weird. You know, what do I mean by you know, the highest scale? Yes, well, what we really mean by the highest scale in the theory is the scale at which we think the standard model is going to be extended. Yes. So what is lambda? Well, so the best physical way to think about lambda is the scale where the standard model is extended with some new physics, the scale where new physics is coming in. Is the scale of new physics. So the modern way of thinking about this is to say that the standard model is actually an effective theory. That has, effective theories always have a cutoff scale in them, meaning that, you know, they are valid below a certain energy range. Yes, we have, for example, right now we have tested the standard model up to of the order of a TeV scale with the LHC. Yes, so we know that the standard model is a valid theory up to essentially the TeV scale, and above that we don't really know what it is, what the right theory is. It could still be the standard model, or it could be some extension. Okay, so this lambda, the way we think about it is the scale at which the standard model gets extended. Okay, the scale of new physics. Okay, so the lambda is the scale of new physics. And what the hierarchy problem, the way to think about the hierarchy problem is to say that actually the Higgs mass is sensitive to the scale of new physics. Okay, so wherever I put this new scale of physics, this calculation is suggesting to you, again, I didn't specify here what the new physics is, yes, but what it's suggesting to you is that the Higgs mass is actually going to be very strongly sensitive, quadratically sensitive to whatever new physics I actually put into the theory. Okay? So the hierarchy problem, the best way to phrase it is that the Higgs mass is sensitive to any new physics. And I will be a little more precise and give you some ideas, what does this actually mean? Okay, so one thing that I would like to set very clear from the beginning is that, the way I originally phrased this calculation is that, oh, there is a quadratic divergence here, and I cut it off, and it's really related to the regulator of the divergences. Okay, but again, now we sort of understand that really, the way to interpret this calculation properly is that, well, actually, it doesn't quite mean that this correction to the Higgs mass is divergent, because really I should have thought of it as an effective theory. This lambda is naturally showing up within that effective theory. Yes, because again, we don't know how far the standard model is going to be valid above the TeV scale, and really, this lambda is just telling you that this is the scale up to which I trust that the standard model is the right description. Okay, so that's what this is standing for. Okay, so some people, start arguing when you see this discussion of the hierarchy problem. Oh, this is something specific about, a cutoff regulator for the standard model. And if I did dimensional regularization, yes, in dimensional regularization, there are no power divergences. And then they would claim that, so that means that there is no hierarchy problem. Yes. So I think those people who say this, they don't fully understand, what the hierarchy problem really means. Yes. Because again, what we are saying is that it's the sensitivity of the new physics. It's not that, a particular diagram is quadratically divergent and I have to choose some regulator. What we are saying is that whenever there is some new physics coming into the theory, yes, there will be a strong sensitivity to that physical mass scale of theory beyond the standard model. And I will show you in a moment a particular, just very simple example how to really understand this well. Okay, but again, so I would say this is really not a reasonable explanation. Yes. Because, again, we are not really talking about a technical issue. We are talking about the dependence. What, if you really understand and interpret this calculation in terms of the effective theory, what you are saying is that there really is going to be a dependence, a quadratic dependence, on any new physical mass scale of the theory that is showing up. So it's going to be a physical object, the Higgs mass, depending on, physical parameters of the theory. Okay, so I'll get to that. Now let me say just one more thing, that at sometimes people are saying, oh, maybe, of course, that's not true anymore because we know what lambda is, but at some point people were saying that, oh, maybe, a solution is that, this particular combination of the couplings just happens to be really small. Yes, and that would actually, so that was the Weltman idea that, oh, okay, so maybe, these are unrelated things in the standard model, but maybe, the Higgs quartic is just such that, it's actually going to be canceling, this loop correction, and then you don't have the hierarchy problem. Now, the thing I would like to say is that on its own is really, again, not a good solution. Yes. So trying to say that, so this is one. idea that I don't think is a very good approach. The other one is, you know, cancellation of one loop, at least without saying, you know, what really the UV completion of the theory is. You know, I was very generous by attaching, you know, a cutoff scale to each of these diagrams, but exactly what that cutoff scale is actually does depend on the UV completion of the theory. It does depend on what actually comes into the theory. And really, you know, if I was more diligent, I would have chosen a different cutoff for this diagram. Basically, you know, whatever physics is cutting off the contributions of the top loops, whatever physics is cutting off the contributions of the gauge loops. So in principle, really the way you should have written this is that you have this 1 over 32 pi squared, and then you have 3 different cutoffs of the theory. 1/4 9g squared plus 3g prime squared times lambda gauge squared, and then minus y top squared times lambda fermion squared. Okay? And a priori, without knowing how this theory is embedded into whatever is coming beyond the standard model, you don't really know whether these cutoffs are exactly equal or not. Yes, so of course I will show you some particular ideas where, you know, from the UV completion, you know, you will know what the relation of these cutoffs are. But a priori, just from the standard model, you don't really know that these cutoffs are exactly equal to each other. Okay, so to just say without anything else that, you know, maybe there's a cancellation, even though numerically it doesn't work. So this was an idea, you know, before people knew exactly what the mass of the Higgs boson is. But so that's also not really a good direction. Okay, so now I would like to come back to this discussion about what I mean by, you know, the Higgs mass being sensitive to new physics. So let me just have the very simplest, you know, stupid idea. Just add another scalar to the theory. Yes, just so that you get an idea what I mean by, you know, this not really being an issue of cutoffs. And so let's just add a new scalar. Let's say S, and complex scalar, doesn't matter, and add some interaction, some quartic interaction between the standard model Higgs and this scalar. Okay? And now there will be a new loop. Yes, so there's the Higgs, and then there's the S running in the loop here. Yes, and then now this is going to be proportional to whatever this quartic self-interaction is. And now you can go ahead and calculate, you know, what this loop is. Of course, this is also quadratically divergent, lambda S over 16 pi squared times lambda squared. But the thing that I would really want to emphasize is that beyond that, there will be a term that is proportional to the mass of this new scalar. Okay, times log. Again, you know, there's a little bit of a cutoff dependence here, but it doesn't matter. Plus finite terms, order ms squared. So these are finite terms. Okay. So there will be terms of the form that are just ms squared over 16 pi squared, no logs at all. Yes. So this is the important point. Yes. That you see that actually what this quadratic divergence really means is that the mass of the Higgs, yes, okay, it's quadratically divergent, but the important part is that it also quadratically depends on the mass of this new particle. So the heavier I take that new particle, yes, the bigger this correction is going to be. That is really the hierarchy problem. Yes, it's not, you know, how do I regulate it? It's the fact that I add some actual new physics, some actual new particles, a new physical scale to the theory. Yes, and the heavier I take that new physical scale, as long as it is talking to the Higgs, yes, it is giving you a bigger and bigger contribution to the mass. Yes, so that's really the hierarchy problem. is the sensitivity to new scales, to new kind of interactions. Okay, so you can ask, okay, what if I added a direct interaction here? What if it's not directly coupled? Yes, you can add just some new heavy fermions that are charged under the standard model. So this is example number 1, example number 2, new heavy fermions not coupled to the Higgs directly at all, but are charged under the standard model gauge interactions, okay? So then you will have diagrams like this. There's the standard model Higgs, yes, and then there's the gauge interactions, and now I can have these heavy fermions running inside the loop here, okay, now, and other diagrams. And now there will be 2 loop contributions, but again, there will be a correction to the mass of the Higgs that is proportional to the mass of these new fermions, whatever they are, yes? Okay, now it's 2 loops, so you get higher powers of the gauge coupling, g to the 4 over 16 pi squared. But again, the important thing is it's quadratically sensitive to whatever I put in to beyond the standard model. Okay, so that's what the hierarchy problem is. If there is, so the way I like to phrase it is, if there is any new physics beyond the standard model, then the Higgs will be quadratically sensitive to the mass scale, to the physical mass scale of that physics beyond the standard model. Now, of course, there's one possibility that is left open there. What if there's no beyond the standard model physics at all? Yes? So if you are willing to believe that, then probably there is no hierarchy problem. I don't believe that there's no new physics at all for several reasons. One is, you have to unify at least at some point with gravity. Yes, gravity is not part of the standard model. And that is a physical mass scale. So that is why you often see, people quoting lambda of the order of m Planck. Yes. So often the way they phrase it is, why is the weak scale so much smaller than the Planck scale? Yes. And the reason why that is because that's one type of new physics that we know for sure at some scale it has to happen. Yes. So should there be BSM? Physics beyond the standard model. I would argue that at the Planck scale, gravity, this is definitely a physical scale. Yes?
When you talk about the cancellation of first loop, you talk about the terminal loop?
I'm talking about, just numerically, these coefficients being very small for some accidental reason. Yeah? So this was something that was proposed, back already, I think, in the 70s by Weltman. And, okay, that's, of course, supersymmetry eventually is going to do something like this for you, yes? But there's a reason why, these cutoffs are also related to each other, okay? So what I was trying to say is that just within the standard model, without any other, addition, I don't think it's reasonable to make that kind of argument.
Free particles, like that. In QCD we have free
asymptotically free particles, yes.
Maybe it is high energy when you have lambda.
But that's okay, but still, this quadratic sensitivity is going to be there, yes. That doesn't really depend on, what, So this is not a QCD, You see, QCD coupling doesn't come in here. Yes, this is the SU2 gauge coupling, this is the U1 coupling, and these are the Yukawa couplings and the quartic. So what I wanted to say is that, okay, if somebody comes and tells you, I don't think there's a hierarchy problem because the standard model is sensible on its own as is, yes, I would say that person is probably right that the standard model is sensible on its own as is. I just don't believe that that is the theory that we are living with because, again, at least there's the Planck scale, yes. Then you also have the issue that if there's no beyond the standard model physics at all, yes, then you really have to take the standard model at face value. At that point, the U1 hypercharge does become strongly coupled at some point. There is a new scale there somewhere really, really far away. But now we are talking about in-principle issues, yes? So there's a Landau pole in U1 hypercharge. It's very high up, but, you know, if you tell me that it's it, yes, really nothing beyond the standard model, then I'm asking, okay, so what happens to hypercharge, yes? Also, you know, why is charge quantized, yes? That's another thing that is very hard to understand within the standard model. Now, people may say it's an accident, but okay, I mean, do you really believe that it's an accident? Okay, so I would say, you know, unification and quantum numbers is probably a good motivation that there is physics beyond the standard model. And of course, you know, dark matter doesn't fit into the standard model. You know, you can go on and on. Baryogenesis, etc. I'm not going to list everything, yes. I'm just telling you that I have a very hard time believing that there's absolutely no physics beyond the standard model. And at any point, you say that there is some new physics with a physical scale, you have the hierarchy problem. Okay. Now, just two more small comments. One other way to just say it, and that's good to understand also, yes, that essentially in the standard model is the Higgs mass parameter that's the only relevant operator. Another way to phrase it is that in the standard model, mh squared is the only relevant mass parameter, only relevant parameter. In terms of RGE kind of classification of the various couplings. So you would think that this is very different than all the other parameters of the theory, yes? So this is in fact, you know, the one that you would expect to quadratically grow in the IR, yes? So another way to phrase it, and this is how Wilson phrased the hierarchy problem, is that it's just very difficult to choose a renormalization group trajectory in which in the IR flows to a theory that has a very light Higgs mass. For most boundary conditions in the UV, if you start the RGE flow of those theories, the Higgs mass is going to be gigantic, basically as large as wherever you started the RGE flows in the UV. Yes? But for some very, very specific ones, yes, there will be you know, a theory with a light Higgs mass. Okay. So the Wilson formulation is that most RGE trajectories will have a very heavy Higgs in the IR. Okay. And one more important comment that I would like to make about the hierarchy problem is that it's specific to elementary scalars. Okay. So it's specific to elementary scalars. What do I mean by that? Well, I was talking to you about corrections to the mass of the Higgs boson, yes? Now, if you're asking, what about the mass of the electron? Yes? Why are we not worried about the same issue about the mass of the electron? What happens if I start calculating the corrections to the mass of the electron? Well, it turns out that the correction to the mass of the electron is actually not proportional to the cutoff of the theory. It's not quadratically divergent or linearly divergent or whatever, not power law divergent, but it's proportional to the mass of the electron itself. There is a little bit of cutoff dependence there through a log divergence, but it's not power law sensitive. Okay? And you can ask the question, why? Yes, why is this so different than the corrections to the mass of the Higgs boson? Yes? And the answer is there is a very good reason, because if I take the mass of the electron to 0, the theory will have a new symmetry. Okay, if you take QED, yes, just quantum electrodynamics, and send the electron mass to 0, yes, there will be a new symmetry, a chiral symmetry. Yes, the left and the right-handed components of the electron, as the only way they couple to each other is through the mass. As once I turn the mass of the electron to 0, I have an independent rotational symmetry of the left-handed and the right-handed components of the electron. Yes? And that symmetry now forbids corrections to the mass of the electron. Yes? So in the limit when the electron mass is 0, there's a symmetry that forbids the corrections to the mass of the electron. Yes? It means that any correction to the mass of the electron must be proportional to the electron mass itself. Yes? Because once it goes to 0, there can be no corrections. That's the only thing that is breaking the chiral symmetry. Okay? So there is a chiral symmetry in the ME goes to 0 limit. And this formula is, again, is not an accident. You can understand it very well. Yes, that, okay, so, and then once the correction of the mass of the electron is proportional to the electron mass, yes, then there is no problem, yes. Okay, yeah, there will be order 1 corrections. You won't be able to exactly explain why the electron mass is 511 keV, yes. But once it's of that order, it will not be destabilized by any new physics. Yes? So in that sense, there is no hierarchy problem there. Okay? And the same, yes? Yeah, absolutely, yeah. So this applies to any fermions, yes. So basically, fermion masses are natural in that sense, yes. Of course, again, as long as the theory is perturbative, yes, as long as perturbation theory makes sense, yes. Yes. Sure. Yeah. I mean, right. I mean, we don't really understand why they are, So we don't really explain. So don't misunderstand me. I'm not saying that we have, that this on its own explains, the different observed fermion masses. Yes. So that's of course another mystery. Yes. I don't know if is Gilad or anybody gonna maybe not about the flavor problem. So the fact that these masses are so different, yes, that's not being explained here. But what is being explained here is that once you have a particular kind of distribution, yes, that's not going to be destabilized by quantum corrections. So sometimes people say this is technically natural, yes. There's still the issue of who told you that the top mass is 10 to the 5 times heavier than the electron mass, or even much more heavier than the neutrino mass? That's another question, yes. And that's a very good question also, yes. And that probably, I mean, most physicists think that there probably is some solution to that, yes. But anyway, so but it does not feed into the hierarchy problem. That's the point here. Okay. Okay, and I also wanted to say that there is the same issue with the W mass, or the gauge boson masses. So gauge boson masses have the same property, yes? What happens if I turn a gauge boson mass to 0? I restore gauge symmetry, yes? Gauge symmetry forbids the generation of gauge boson masses. So it's the same story, yes? So the corrections to the W mass, yes, are going to be proportional to, basically all the, I can schematically say mw squared, but really it means, whatever the Higgs wave is, it's going to be proportional to the Higgs parameters of the theory, yes. So again, in the limit when mw goes to 0, the gauge symmetry is restored. And again, it's a schematic. There's probably mixing between the W and the Z masses, but and the gauge symmetry is restored. So again, you don't have that hierarchy problem. Okay, very good. So a few last comments. So what are possible ways out? What are the possible type of solutions? Well, So the type of solutions I'm going to be talking about, and that's sort of the traditional direction, is that, the problem is that lambda much bigger than the TV, yes? And that we understand what this means, that lambda is the scale of new physics, yes? So the best solution is to say, well, okay, so let's just not take lambda to be much bigger than the TV scale. Let's assume that lambda is of the order of the TV scale, yes? Then, of course, you don't have this hierarchy problem. So that would mean that there is new physics at the TV scale. So then that would make these relations about the corrections to the mass of the Higgs boson natural, yes, at least from the point of view of the new physics. But that's, of course, not enough, yes. That new physics has to be special. It has to be such that once I introduce that new physics, it gets rid of the sensitivity. It eliminates the sensitivity of further corrections to the Higgs mass. So it's got to be something special that will then shield the mass of the Higgs boson to corrections beyond the scale where this new physics came in. Okay, so that's the traditional way. So this is, for example, how supersymmetry and composite Higgs is going to work. Okay, so there is new physics at the TV scale, and that new physics is special. Physics will then shield the Higgs from further corrections. So again, the idea is that these kind of corrections that I wrote down here, that those would actually be there, yes, but lambda is set to 1 TeV, or 2 TeV, or 3 TeV, or something like that. Yes, all of these lambdas are set to a few TeV. So those corrections are actually there, yes, but they are not unnatural because lambda is low enough. Yes. So there will be new particles coming in, or new physics at that low scale. It does, in fact, correct the Higgs potential, yes, but that's okay because it's not too large, yes. But then the important thing is that this new physics is special, that any correction beyond that is not going to be sensitive. Once you introduce those new particles, there will be no more sensitivity to the very high scales above where these new particles came in. Okay, so that would be sort of the traditional way of solving the hierarchy problem with new physics at the TV scale. And again, so the ideas are, and we will be discussing this in great detail, is supersymmetry. And let me just quickly say how, why supersymmetry works. And of course, the rest of the lecture will be to go into great detail of explaining what supersymmetry is. But the main idea with respect to the hierarchy problem is that, as you will see, supersymmetry will sort of unify fermionic and bosonic degrees of freedom. Okay, so there will be new particles at the TeV scale, which we call superpartners. And again, these, if you don't understand, exactly what superpartner mean, that's what I will be explaining in the next few lectures, so that's okay. But again, I'm just trying to sort of fit this into the scheme that I'm telling you about the hierarchy problem. So there will be all these new particles, these superpartners. They come in at the TeV scale, and there will be this relation between fermions and bosons. So the superpartners will be relating fermions and bosons to each other. And the trick will be that the fermions, we know, don't have a hierarchy problem, yes, by the way that I just explained it here, by chiral symmetries. And now there will be a new symmetry that is relating the fermions to the bosons. So this one is not having a hierarchy problem because it's chiral. Yes? And then supersymmetry will ensure that the superpartners of those particles, yes, also don't have a hierarchy problem. Of course, again, you know, this is what I'm going to be explaining. So this is a very rough, just to give you, you know, a preview of where we are heading. Okay. So Susie is actually not directly one that is getting rid of the quadratic divergences, but it's Susie combined with the chiral symmetry of the superpartners is what is going to be protecting the Higgs from large corrections. Okay. So that's one sub-direction here. And the other one, you know, is based on Goldstone's theorem. So that's going to be the lectures, the second half of the week. Yes. So what we say is that there is a way for us to make bosons very light, in particular massless, yes, if they are Goldstone bosons. Yes, Goldstone's theorem does make, you know, bosonic scalar degrees of freedom massless. So if you have a broken, spontaneously broken global symmetry, if you have a broken global symmetry, yes, you will have massless scalars. And then the task is, and that's what we will be spending our lectures on Thursday and Friday on, is how to lift this idea of having Goldstone bosons to apply to the Higgs. That's because, you know, Goldstone bosons are great, but they are massless. They have very specific kind of couplings, not the kind that the Higgs has. Yes? So how do we make the Higgs look like the Higgs at the same time and look like a Goldstone boson at the other time? Yes. Now, a very related idea is compositeness. So we will see in these lectures that, in fact, in some sense, you know, all this idea of the Higgs being a Goldstone boson and compositeness, they go together. Okay, but here the idea is that there is no elementary scalar. There is no true elementary scalar. The Higgs is a composite of, for example, some fermions or some more fundamental degrees of freedom which don't have a hierarchy problem. Yes? So then the only thing that you need to explain is the hierarchy between the scale where these guys became composite and the actual observed mass scale of the Higgs boson. Okay, so compositeness would say that the Higgs is not an element. No, we measured it. It looks like an elementary scalar, but in reality, it's not. At some higher scale, you know, just like the proton, it originally looked like an elementary particle, but actually it's not. It has some constituents, and if the constituents of the Higgs, you know, actually are not scalars themselves, but fermions, which of course is possible, then there wouldn't be a hierarchy problem. Okay? But it turns out that, you know, these two actually will go hand in hand, and the two together will be, you know, what is sort of, you know, in this more modern literature is called the composite pseudo-Goldstone boson Higgs. Now, another related idea, and hopefully I will have time for that is warped extra dimensions. And it turns out that these two ideas are essentially the same. That one is a four-dimensional effective field theory description, and the other is a description via holography. And maybe we will have time to discuss that. So holography is connecting these two ideas. Okay, so it turns out that they are really not that different, and and, you know, we'll hopefully see, you know, how they are related to each other. Now, a few more radical ideas. And some of it was actually, you know, the first one. So there's something that is called technicolor. And in this type of models, so now these are dead, yes, there was actually no Higgs at all, but the electroweak symmetry was dynamically broken. Just like in QCD, so you probably know that the QCD is a strongly coupled theory, of course, and in the vacuum, there are quark condensates. It's a theory without elementary scalars. It just has quarks and gluons. But because of the strong interactions in the vacuum, the structure of the vacuum is much more complicated than a perturbative weakly coupled theory. And the vacuum actually does produce condensates of the quarks. And those quark condensates actually in QCD do break the electroweak symmetry. So that's how this idea came up first. Okay? And we will probably talk a little bit about this when we talk about the composite story. So QCD breaks the electroweak symmetry. Okay? So even if there was no Higgs, yes, the W and the Z would not be massless. Yes, there would be a little bit of a mass for the W and the Z, except the scale would be set by the scale of the strong interactions, by the scale of lambda QCD, the scale of the proton mass. So there would be a little bit of a W and the Z mass, but it would be of the order of a GeV, and not 80 or 90 GeV. Okay, so the idea of Technicolor was to say, okay, well, then let's make another strong interaction type theory now with the right scale, yes? Okay, let's just take QCD and put another version of QCD that would give me the right W and Z mass, so let's make it at 100 GeV. Yes? And then that would be, again, that's why it's Technicolor, yes, because color is the usual theory of strong interaction, and Technicolor is sort of an even stronger version of it, and then that would have given rise to electroweak symmetry breaking. Of course, the problem with this is that, well, this doesn't have a Higgs, yes? So it doesn't have a Higgs. Well, what's the thing that has been observed at the LHC? There are still some diehard people who wouldn't take no for an answer, and they would claim that maybe there are naturally some degrees of freedom in the theory that will look like the Higgs, but I find that really not very credible. Okay. Now then there was another interesting direction that was called large extra dimensions. So that's the direction that is very different from the warp extra dimensions. So the warp extra dimensions, again, goes together with all of this compositeness and Goldstone boson. The large extra dimension, so this is a model of Arkani, Hamed, Dimopoulos, and Douali. So it's called the ADD model from '98. So here, they sort of turned the hierarchy problem around and said, well, what we are really interested in is, why is, the weak scale so different from the other scales of the theory? And they tried to come up with a theory that has only one fundamental scale. So the idea here is that actually there's only one fundamental scale. And that, of course, well, we know that the weak scale is a real scale, real physical scale. So then if that's the case, then the weak scale has to be the fundamental scale. And then, of course, you wouldn't worry. Yes, that's the only scale in the theory. Of course, then the question is, but then what is M Planck? Yes, where does M Planck come from? Yes, so they made up now a theory for sort of having an effective Planck scale, yes, that will look much larger than the weak scale, yes, even though the fundamental scale of gravity is also the weak scale. Okay, so that was the idea of the story of large extra dimensions. I'm not going to talk very much about it. It's a fun story also, it's a different approach. I mean, I would still say it's in the approach that, you know, there is some new physics at the TeV scale. It's just, you know, doesn't fit into these two big classifications. Of course, you know, then there are other ways, and I will not talk about those now because that's what Raffaele is going to be talking about. So the more sort of more modern approaches, and you'll see that next week. Most recent ideas. See Raffaele, but just to give you, you know, just a few words about it. So the idea there is that, you know, maybe, you know, there is some, you know, completely different approach here. Here we always assume that there's a new physics at the TeV, and that will solve the hierarchy problem. But there, you know, these new directions are usually related to some cosmic selection of the weak scale. And there are different kind of ideas, different kind of directions. One could be that there's just one universe, but, you know, the Higgs mass parameter, this mu Higgs mass parameter is in fact, you know, changing as the universe is evolving, expanding, etc. And then something very special happens when the Higgs mass parameter is very small and it's actually just undergone electroweak symmetry breaking. So that's like the relaxion type idea. And I presume that special happens when, you know, the Higgs wave is very small, but non-zero is less than the TeV scale. So somehow, you know, this scanning of the Higgs mass parameter stops because of the electroweak phase transition. Okay, so that could be one direction. Another direction is that there may be many different universes, and in fact, you know, the Higgs mass parameters are different in those universes, but for some reason, the ones where the you know, where the Higgs mass parameter is not giving rise to light Higgs bosons are just dynamically unstable and they just crunch. Okay, so there could be directions where, you know, there are many universes. But the ones with very different properties are just short-lived. Okay. So I worked on some of these ideas, and, you know, they are fun. And the important thing is that these have very, very different experimental predictions than the traditional ones that I will be talking about in these lectures. So, you know, those are the ones that the LHC is really starting to, you know, put a strong pressure on us. So then the theorists, of course, try to go in other directions and see. So what other ways are there that, you know, would not have been already excluded or put under pressure by the LHC? And then, of course, you know, there's the other, the extreme of this, yes, is where you say, well, there are many, many universes, and they, in fact, have different Higgs masses, and they are just sitting there, except, you know, the ones where the Higgs mass is so different from us, you know, just won't have observers. So that's sort of the anthropic approach. So that's, I guess, the real extreme. It says, yeah, there's, you know, all of these are sort of equally possible, except in the ones where, you know, we don't have a universe that looks like ours, you know, we won't have observers, so, you know, we just won't be able to ask the question of, you know, why the Higgs mass is light. Okay, I mean, I'm not very excited about that, but since I don't really know what kind of physics questions I would be asking there, though, you know, it's not, maybe not as crazy as it sounds, because, you know, what Nima always says is that, okay, so in this anthropic approach, you really need to have a lot of different vacua to have everything realized, and for that, you have to have a lot of scalar fields, and while, you know, of course, the other vacua you will not be able to communicate with, but just the fact that you have like 100 scalar fields, yes, you should be able to measure within our universe, okay? So maybe it's not as, you know, the outlook experimentally is maybe not as negative as I initially thought, you know. Of course, you know, we won't be able to see all these other vacua, but we could maybe, you know, at least in principle, we could measure the potential of all these other scalar fields and see that other potential vacua do exist. So that's something that in principle we should be able to do within our universe. But anyway, I mean, it's starting to get far away from my, my main topic, so I just wanted to give you this overview of what the different ideas are. But the plan is that in my lectures, again, you know, we are going to be first focusing on supersymmetry, and then on Goldstone's theorem and compositeness. So before I start with Susie, any questions now before I make the transition? Yes?
So I may have to, in relation to Wilsonian approaches. So you say that we expect the Higgs mass to be very large because you're expecting a Higgs mass of order 1 at the Planck's.
No, I'm just, no, that's not what I said, yes. I said that, you know, you expect there to be some RG trajectory. You start out at some high scale in the UV, yes. Could be the Planck scale, could be 10 to the 10 GeV, whatever. Yes, and in most RG trajectories, the Higgs mass is going to, you know, grow with a power law of the scale, yes. So in most of those trajectories, you expect it to be as large as wherever you started out with. If you started with some boundary conditions that seem natural at the UV, yes, just some random boundary conditions. Yes. Okay. Now, it doesn't mean that there is no RG trajectory. Yes. It's like, you know, the standard model on its own is a sensible theory. Yes. You can fine-tune the Higgs mass to be where it is. Yes. So I did never claim that the standard model is not a sensible theory. Yes. It is. And again, if you don't try to add any new physics ever, you probably will never run into the hierarchy problem. So the people who only do calculations within the standard model, yes, they may never discover the hierarchy problem. And then they keep telling me, but I did all these calculations. They make all sense. Where is the problem? Yes?
Yeah, I mean, the point is that right now it's being revived, the whole thing, the comparison between Wilsonian approaches. And so there was this paper by Csaba Csaki in October and now again, and so on. And they claim that, I mean, that it's discussed that Wilsonian approaches see that these are kind of
again, you know,
trajectories, and I mean, anyway, you should find there should be no problem with the Higgs mass being small.
I think, you know, Shaposhnikov already said many different things why there shouldn't be a hierarchy problem. So I think I'm going to leave it at that point.
Okay, and then another question is like, what is the Higgs mass in the symmetric phase? I mean, what you are discussing is this parameter that enters in the.
Right. In the symmetric phase, you know, there wouldn't be a Higgs. Well, I mean, there wouldn't be electroweak symmetry breaking, yes? And the whole doublet would just have the mass mu, yes? Very heavy, no mass to the W, okay.
It's kind of a complex mass, right? I mean, can we understand this as a state which has a very large decay width, or I do not understand.
Sorry, I mean, you know, if the symmetry is not broken, yes, you have a complex scalar. Yeah, it's a very heavy object. You know, yeah, it will probably decay to. I mean, the top is massless, yes, because it didn't get a mass from anything. You know, so yeah, the Higgs will probably decay to 2 tops. Yeah, that's okay. I mean, it's just not our world, yes? Yes? Yes. So it will all, it will have its own hierarchy problem, yes? So I just gave it to you as an example to, not because I think that that's a good model beyond, I just wanted to show you that, introducing a new physical particle will give you a correction to the Higgs mass that is proportional to the physical scale of the theory, yes? So what I was telling you is even if you forget about the lambda, yes, the finite contributions, yes, the ones that are proportional to ms squared, yes, as long as that mass is much higher, yes, we'll want to pull the Higgs mass up to the same scale where this other particle is. That was the idea. But yes, of course, that ms will have its own hierarchy problem, But of course, then, I gave you another one where you had only fermions, and then that one wouldn't have a new hierarchy problem. Yes. Again, it was just illustration. I'm sorry? Right. That's what I was saying, yes, that it's particular for elementary scalars. Yes. If they are composite, again, then, it may get cut off at the scale of compositeness. Yes. It's elementary scalars. Yes?
It seems that that three options that we have, the first one is that we can physically try to understand. We can probe, twist.
Which one? Sorry, are you talking about?
The mass of the Higgs is changed.
Right, right.
That's the more physical one.
Right, but it's changing during cosmology, yes?
Yeah.
So now, of course, it's not changing anymore, yes? So the idea was that, again, I think Raphael, it was very, very schematic, but the
The universe is that mass is given by no.
so the universe is expanding, there was some field that was changing, yes, and in very early epochs, there may not have been an electroweak symmetry breaking at all, yes.
But how could we try to get back this information?
That's a good question. Yeah. So from the very early epochs, I'm not sure whether there is any, but again, the mechanism that makes this whole thing stop,
Yeah.
that's what you would be focusing on. Yes.
Yeah.
So that's the idea that. But anyway, that's something you should. Yes, in Raffaele, yes.
I think it's actually Gilad, but
I'm sorry. There's also something with.
Gilad
He's doing relaxion, and what is Raffaele doing?
Gilad is not a
What is Raffaele doing?
it's an axiom.
Okay, whatever.
It's one
Next week. Next week.
one of them.
All right. Ready for supersymmetry? Yes. One more.
I guess you can measure the change of the mass with the electric phase transition that may be happening in the universe by the measures that can be made.
Right. But I don't know. Well, okay. So of course, there. So I don't know that how much people have studied that. Whether it would be different than in the standard electroweak phase transition. So probably. But I don't want to be committing since I haven't studied that subject. So, all right, supersymmetry. So let's see. Where did So our next big topic is supersymmetry. So again, this is one of these basic ideas that are giving you a specific kind of extension of the standard model, yes, where the new scale would be coming in at a low scale, and that new physics is very special in the sense that once these new particles are there, together they are going to shield the standard model from any corrections beyond the scale where these new particles have come in. Okay. So I'm going to try to, so I go back and try to explain supersymmetry from the beginning, so you will hopefully understand all the basics, but this is where we are heading at least. Okay, so what is supersymmetry? So first, let's try to remind ourselves, what is an ordinary symmetry? Okay, what's an ordinary symmetry? Yes, well, in an ordinary symmetry, we take the fields of our theory, and then we do some sort of a transformation that leaves the Lagrangian or the action invariant. Yes, that's what a symmetry is. So I do some transformation, some delta phi, yes, where this delta phi is some linear combination of all the fields. Yes, so this delta phi is some linear combination of the fields in the theory, T-A-I-J, epsilon A with an I. Yes, so this would be the generators of the symmetry. Yes. It's just saying again, you know, that I take some linear combinations. Yes, this epsilon is telling you, you know, how much of a rotation I did. So these epsilons are the rotation parameters. They're telling you how much rotation I did in this internal space of the fields. Yes. So you can have like two fields and then, you know, just do a rotation. Yes, a little bit of a rotation, and then you can find what the generators of the theory are. Yes. Now, so these are the generators, and the main assumption of symmetries that we have, you know, that ordinary symmetries have is that you mix bosons with bosons and fermions with fermions, but you don't mix those two with each other. Okay, so phi go to phi, so these are all going to bosons with bosons or fermions with fermions, which means that these generators, these TAs, the generators of the symmetries, like, you know, the SU2 of the electroweak symmetry, or you know, any flavor symmetry that you may have, global symmetries, yes, that these are bosonic. Yes, so the TA are usually bosonic. And again, what that means is that, you know, they satisfy some sort of an algebra, and this algebra is given by the commutators of the generators times FABC, yes. So they form some sort of an algebra, and that is telling you what the how the different generators, if you act with the different generators in different order, yes, what the result is going to be. So this is essentially telling you what the nature of the symmetry is. So supersymmetry is very much like an ordinary symmetry, except that the generators themselves are fermionic. Okay? So the main difference between supersymmetry and ordinary, let's call it now bosonic symmetry, yes, ordinary symmetries, yes, are that these generators are fermionic. Okay, so what that will tell you is that when you do a symmetry transformation, you're actually going to be mixing up fermions and bosons with each other. Okay, so that's quite different than, again, what we are usually used to. Okay, so we are mixing up fermions and bosons. Now, in ordinary symmetries, once you know what the symmetry of the theory is, you want to sort of group the different fields into representations. Those are the basic building blocks of that symmetry, yes? So you usually have representations of the symmetry. And so those are the basic building blocks, like, for example, when you have QCD, yes, you have quarks, and they form a triplet of QCD. Yes, the gluons are forming an octet of QCD. Yes, so those are the basic building blocks. And you will have similar kind of basic building blocks for supersymmetry, but now those different building blocks will contain both fermions and bosons at the same time. Okay, so that's going to be the big difference. Now, let me just give you a little bit of a history. So this is something that people have been thinking about in the 1960s, because the 1960s was really successful in sort of, finding these symmetries and starting to put them into representations like Gell-Mann did for SU3. There was the eightfold way. And people tried to extend that to include both SU3 of Gell-Mann and spin, ordinary spin of Lorentz transformations, yes. And that was a big failure. So initially, people thought that they actually found a no-go theorem. Yes, that one was called the Coleman-Mandula theorem. And that was telling you that actually that it's really not possible to have some non-trivial combination of the internal symmetries of the theory with the space-time symmetries, with the Lorentz symmetries of the theory. So to unify internal symmetries with Lorentz. And of course, all of these no-go theorems, they have some pretty, strong assumptions. And then later in the very early 70s, people realized that there is actually one exception. Okay. And that one was actually found by Haag, Lopushansky, and Sonius. That's just a little history. There is one non-trivial way to avoid the Coleman-Mandula theorem, and that's when, again, the generators themselves will form what is called the graded Lie algebra. The generators themselves are fermionic. And they will, instead of having these commutators, those fermionic generators will obey some anti-commutators. Okay, so this will be Q is going to be standing for the generators of supersymmetry. So those will be the analogs of the TAs, but for supersymmetry. And now these are fermionic, yes. So they should carry some Lorentz index. So this is a Lorentz index. So this is a Lorentz index. Okay, and there could be, in principle, there could be several of these generators. So for now, I'm allowing it, but later on, I will just restrict myself to have one of these, yes? And now this one is going to form actually an anti-commutator with the complex conjugate of this supercharge. So this is the generator again. So what does this mean? So alpha is a Lorentz index. So this is a 2-index Wild spinor, yes. The complex conjugate of that Q has a dotted index under Lorentz transformations, yes. So this is, if this is a SU, this is the SU2 cross SU2 symmetry. If this is the left-handed guy, then this becomes a right-handed guy. Okay, and there was one possible way to close this algebra into the existing symmetries, and that's what this theorem is telling you. I'm not going to try to prove it here. There was one possible way of closing this algebra with the existing space-time symmetries of a quantum field theory. Well, so you see this has an index alpha, alpha dot, so there has to be something that carries an index alpha, alpha dot. So that's, you can take the Pauli matrices here, and the Pauli matrix then has a vector index mu, and then this can close with the ordinary momentum of the Poincare symmetry. And then there is a normalization here too, and then there's these other indices, delta Lm. Okay. So again, just to be sure that we understand what this means, yes. So this is essentially what the SUSY algebra is. Okay, there are other, commutators, but they are all essentially trivial. This is the crucial one, yes. So there's a new type of symmetry, yes. This is Q. So this is, when it acts on a boson, it makes a fermion out of it. When it acts on a fermion, it makes a boson out of it, yes. It carries a Lorentz index, so that also, you want to maintain the spin statistics, yes. So if you have a fermionic generator, it better carries a Lorentz index, because out of a boson, it makes a fermion, yes. So now you think that it better carries a Lorentz index, yes. And then instead of a commutator, you will have an anti-commutator, because these are fermionic charges, yes. And again, what you want is that it has some non-trivial relation with the other already known symmetries of your theory, yes. So the way you can make this consistent is by using the translation, the generators of translation, the momentum of the theory, and these sigmas here are just the Pauli matrices, yes. So the sigmas are the Pauli matrices, and I don't know, yes.
Wouldn't it be more conventional to call these spinor indices alpha, alpha, as
Spinor.
opposed to mu?
Sorry?
As opposed to mu, which is this space-time index.
These are spinor indices here, yes.
Spinor
Spinor
indices.
indices, yes.
You call them Lorentz index.
Lorentz, spinor, whatever, yes.
I would call mu Lorentz index.
Spinor, yeah. Sorry, I call
Just so
everything,
people
yeah.
don't get
Yes,
confused.
while spinor, yes.
Otherwise, you
Yes.
could say G
Yeah.
K U, G
Yeah. So this is a 4-vector index, yes. This is a 4-vector index. Yeah, so this one runs from, from 0, 1, 2, 3, and then these are indices, and so you know that the Lorentz group is SO 3, 1 or 1, 3 or whatever, is essentially like an SU2 cross SU2. And so this would be, so the Q alpha, yes, this alpha, the spinor index is a 1/2 0 representation of SU2 cross SU2. And then the dotted one, yes, that will flip the left and the right. Yes, so these are, okay, yeah. So these are spinor type indices under the Lorentz group, yes. Okay, very good. And again, so these are anti-commutators, yes, and they are closing into the usual space-time symmetries. And you can write down all the other generators, all the other commutation relations. That's not super important, but essentially Q is going to commute. So if you have a fermionic and a bosonic symmetry, then you would want to write a commutator. So that's a 0 with the generators of boosts and rotations. There will be a non-trivial commutator here, and this is equal to -I sigma mu nu alpha beta q beta A. Okay, and then 2 generators, 2 SUSY generators. If you take their anti-commutator, if if there's only one, then of course it's going to be 0. If there's more than one, then it can have some non-trivial, what is called a central charge, but it doesn't matter very much. Okay? So the upshot is that there's this beast here, yes, this supersymmetry algebra that is a generalization of our notion of symmetries. Yes. And when you try to analyze what it means to have the symmetry, you will find quite different properties for the basic building blocks. Okay, so for example, let me just show you one very nice property. If the theory is supersymmetric, if you have SUSY, so if you have a generator like that is implemented in your theory, then the number of fermions equals to the number of bosons. Not very shocking, yes, because it's telling you that there's a symmetry that relates fermions and bosons to each other, yes. So you would expect that, they are now somehow on equal footing, yes. So at least, their numbers should be equal. So let's do this one proof carefully, and then the rest I'm going to just list, and maybe we can put that as homework. Okay, so number of fermions equals the number of bosons. So the way to prove this is to introduce the fermion number operator. So this -1 to the NF, so this is the fermion number operator. And essentially, the way it's defined is that if it sees a bosonic state, then it just gives back the bosonic state. And if it sees a fermionic state, then it gives -1 times the fermionic state. Okay, so it's telling you, is this a fermion or is this a boson? So that's the fermion number operator. Yes. And so let's take now a state, an arbitrary state in our system, yes, and act with it on my supercharge. Yes, so if this was fermion, it made a boson out of it. If it was boson, it made a fermion. Yes, and now let's try to check what is the fermion number of this combined state. Yes, since the supercharge flipped the fermionness, yes, or whatever the statistics of the state, yes, whatever it was, it's going to be the opposite, yes. It's going to be minus Q alpha A times -1 to the NF times Q, yes, because if it was a fermion, it made a boson out of it. So if I first measure whether it's a fermion or a boson, yes, the Q is going to give me the opposite. Okay, so that tells me, yes, now I can bring it to the same side. So this is telling me that the fermion number operator and the supercharges anti-commute with each other. So -1 to the NF and Q alpha A anti-commutator is vanishing. Yes, it's just, I bring it to the same side. So now it's the sum, yes, and it's on any state. Yes, so that the only way that's possible is if you have this operator identity. Okay, so now let me do a trick. Yes, let me take now the trace over, whatever, one building block, one representation of supersymmetry of -1 to the fermion, so the fermion number operator, and then that commutator over there. Yeah, sorry, the basic anti-commutator of supersymmetry, Q alpha A, Q bar, beta dot B. Okay, let's take this trace. Yeah, so trace of the product of these three operators. I can just start writing it out. Yes, it's -1 to the NF times Q alpha A, Q bar, beta dot B. plus minus 1 to the NF times Q bar beta dot B Q alpha A. Yes. And then the trace of this. Yes. But now because it's a trace, I can do cyclic permutations. Yes. So I can take, one of these, I can move to the front, for example. Yes. And then I can also do my anti-commutators of minus 1 to the NF, the one that I just calculated here. Yes, I can flip a sign. Yes, so I can bring one in front. Yes, and then flip the sign, flip the ordering. Then I will flip the sign, and you will see that this is actually 0. Yes, the two terms cancel each other. So I do first the cyclic permutation, and then I will flip these two operators by this anti-commutator. This whole thing is equal to 0. Yes, so the trace is cyclic. Yes, so this one is actually 0. Yes. On the other hand, I know what this basic anti-commutator is. Yes, it's just 2 p mu times sigma alpha alpha dot mu times delta LM, delta AB. Yes. So now what I'm going to get is that the trace of minus 1 to the NF times 2 p mu times whatever, the sigma mu alpha alpha dot times delta AB is equal to 0. Yes. And this is supposed to be for one representation. Yes. So these things can come out of the trace. Yes. And what you're going to find is that trace minus 1 to the NF is equal to 0. Okay? So that means that if you trace over a representation, then the fermion number, the sum of it is going to be 0. Yeah? So that means that you have an equal number of fermions and bosons. And so this is a nice game, and you can play several of these nice games. And I'm just going to tell you a few more basic results that, again, just very similarly to this, you can obtain that, not only are there equal number of fermions and bosons, but within one representation, the masses are equal. Yeah, so within one representation, one basic building block for supersymmetry, you have an equal number of fermions and bosons, and they have the same mass. And the third important property, though we won't use it too much here, but it's just conceptually very important, that the energy is positive definite for supersymmetric theories. Energy is positive definite. So if you take any state and the Hamiltonian, that's going to be positive. And in the ground state or whatever. And if supersymmetry is unbroken, then the vacuum energy is exactly 0. So the vacuum energy is an order parameter for supersymmetry breaking. That, of course, would be fantastic for the cosmological constant problem, except, of course, supersymmetry is broken, and that's that relation only holds when SUSY is unbroken. So I have 5 more minutes, or how much do I have? Something like that. 5 more? Okay. So let me just get to a good point. I'm sorry? 45. Oh, it goes until 45, not 30. Okay, so this is also a good point to stop. So the next thing I will do is I will tell you what the basic representations of supersymmetry are and how to write this in terms of a Lagrangian, and hopefully by the end of next lecture we will write down the Lagrangian for the extension of the supersymmetric of the standard model, which is called the MSSM, and then I start to understand, what kind of particles, what kind of interactions there are, how is supersymmetry broken, and then, at some point, what the problems with supersymmetric theories are. All right, so let's stop here, and time for questions, and then I guess we'll see each other tomorrow. I think I'm in the afternoon tomorrow, or I keep
Second
forgetting.
talk in the morning, I believe.
Second talk in the
But-
morning, okay.
Okay,
So questions? Yes?
So does this theorem about geometry and etc. tell us also that we can't go further?
Yes. So the claim is that this is it, that there is no more. The only thing that you can have is several of the supercharges and nothing else. So there is no...
So no vector.
Exactly. So no other non-trivial extensions. And of course, this has also some assumptions I forgot. It has to be interacting, I think, this is like the most general thing that allows non-trivial interactions. I think, if you have just free fields, probably you can do a lot of things, but not very interesting.
I think it's also just for unbroken.
Just for?
Unbroken. There's some problem in it spontaneously broken.
I don't know. Good question. Yes, up there.
I think you should use
We'll have the microphone because
Yes,
then
okay.
the questions
Yeah,
are
yeah.
recorded as well. It's better.
Hello. I have a non-technical question because before starting my studies, people told me not to study supersymmetry very deeply because the community was willing to abandon this idea because CERN found no evidence of superpartners and
So
those things.
that's definitely true, yes, that this idea of supersymmetry on its own, is starting to be challenged. It will never really be excluded completely in the sense that, you can always push the superpartners to higher masses. But, okay, so then the real question is, should you still learn about supersymmetry?
Yes.
And I would say, absolutely. When I have students, I always tell them, the first thing you should learn is supersymmetry. Probably it's possible that we won't do too many projects directly on building models beyond the standard model anymore that are supersymmetric. But to really understand the idea of what it means to have a coherent theory beyond the standard model, where all the problems are really clearly laid out to you. What are the new particles? What are the corrections to the Higgs potential? What's the flavor problem? How does it show up? Yes, you understand best in the case of supersymmetry. That's one reason why I tell them. The other reason why I tell them that you should still learn about supersymmetry is that it's really a great laboratory for understanding strong dynamics. So that's what I usually use it for now. So it's very hard to understand QCD, because it's a strongly coupled theory. But as it turns out, the supersymmetric versions of strongly coupled theories are often much more easily understood. So I would say, that's another very clear motivation for doing it. But I would say the main motivation is really all the concepts of what it means to even have a BSM theory. That's where you understand it best. So now, of course, there are other reasons, string theory comes, supersymmetry. So at some scale, we think there will be supersymmetry. Yes, but that may not be a strong enough motivation if it's, very, very high. We may never see it. Yes, but it probably is going to be the, part of whatever the final theory ever is. I would think. Also, it's the biggest space-time symmetry that you can have. Yes, for physicists, that's pretty good motivation also.
Thank you.
But yeah, I wanted to say this. I forgot. Thanks for reminding me.
It was a great question.
Yes.
I think we should probably break for coffee. Now, did I read correctly that we have 15 minutes coffee break?
Very short.
Very tough. So the coffee is just outside upstairs. If you turn left, there's stairs that go up. So let's thank Csaba once again for this wonderful first lecture.
Good.
time is extended.